Hi everyone, welcome back to Math TV with Professor V. I'm saying welcome back because this is part 2 of the review for Calculus 1 final exam video that I first published yesterday. So I got so much excitement and feedback about part 1. Let's just jump into part 2. We left off at implicit differentiation. So I have a couple examples for you guys. Use implicit differentiation to find dy dx. The main thing you need to keep in mind is implicit differentiation is just an application of the chain rule. So anytime you differentiate a variable, and it's not the variable that you're differentiating with respect to, then you need to multiply by d whatever it is dx. What do I mean by that? Watch and see. So here we have cosine of x times y plus x to the fifth equals y to the fifth. So here's how you got to think about it. What's the derivative of cosine something? Why, it's negative sine something. Okay, great. So negative sine, here's the something. I'm not touching it. And then the chain rule tells me now I'm going to multiply by the derivative of the something, namely xy. Well, derivative of x times y, I need to bust out the product rule, right? Because we have a product of two functions. Both x and y are variables. So here we go, product rule time. Derivative of x is 1 times, I'm going to leave y alone. Remember, they take turns when they have their derivative taken with the product rule. Plus, then I'm going to leave x alone. And then what's the derivative of y? Well, it's 1, but then I need to multiply by dy dx. Why is that? Because I'm differentiating y with respect to x. Really, when we took the derivative of x here and it was just 1, we did multiply by dx dx. You just didn't see it because that's 1. So when you take the derivative of some variable and it's not the variable that you're differentiating with respect to, you have to have d whatever this is, dx in this case, okay? Good. Plus derivative of x to the fifth. So that's 5x to the fourth. And then, there is a dx dx that you don't see equals derivative of y to the fifth. It's 5y to the fourth times dy dx. That one we see. All right, now all the calculus is done. So it's just a matter of can you solve for dy dx. I see dy dx here and here, 2 places. So let's put all the terms that have dy dx on the same side of the equation. In order to do that, I'm going to need to distribute negative sine of xy first. So to not make it confusing, I'm going to write negative y times sine of xy minus x times sine of xy dy dx plus 5x to the fourth equals 5y to the fourth dy dx. And then, these 2 terms are yearning to be together. So let's make their dreams come true. I'm going to write negative y sine of xy plus 5x to the fourth equals x sine of xy dy dx plus 5y to the fourth dy dx. And what's the point of putting everybody with a dy dx together? So you can factor out dy dx, and then we're going to have x sine of xy plus 5y to the fourth. On the other side, you know what would be so snazzy? Let's write 5x to the fourth minus y sine of xy. Nobody likes a negative sticking out in the front. Such an eyesore. And then now we're going to divide both sides by this quantity. I don't need to write it out. You're all calculus students. So we can move on to the final step right now. We'll have 5x to the fourth minus y sine of xy over... Oh, it'll look so nice if I put the 5y to the fourth first, wouldn't it? Yes. Good. So there's our final answer, and we've written it in the most aesthetically pleasing form possible. How fabulous. Okay, let's try another one. This time we have to find not only the first derivative, but look, the second derivative as well. Ooh, how exciting. Now, the directions say that we have to use implicit differentiation. You could, in this particular case, solve for y, isolate it, and then just take the derivative directly without using implicit. But we're going to be obedient. That's part of being a successful math student, following the directions. Okay, derivative of x squared, 2x. Derivative of negative y cubed, negative 3y squared times dy dx. Good. Derivative of 6, my favorite, 0. Okay, in this case, it's a lot easier to solve for dy dx. We just have negative 3y squared, dy dx equals negative 2x. And then I'll divide both sides by negative 3y squared. So we have dy dx equals positive 2x over 3y squared. Fabulous. All right. Now, again, we're going to have to differentiate with respect to x. So to do that, I'm going to take the derivative with respect to x of dy dx. Look at dy dx. It's a quotient, right, of two functions, 2x and 3y squared. So time to use the quotient rule. Sing along with me. We've got low d high. What's derivative of the numerator? 2. Very good. Minus high d low. Please be careful. Derivative of the denominator is 6y times dy dx. Good. See? Over low low. So square the denominator. That's 9y to the 4th. Okay, good. Now cleanup crew comes in. Let's clean this sucker up. So numerator is going to be 6y squared minus 12xy. Oh no, we don't leave dy dx. We replace it with what it's equal to, namely 2x over 3y squared. And then we still have 9y to the 4th down there. Okay. Let's see how this simplifies further. So we've got 6y squared minus 12xy, that's in the numerator, right? So it'll cancel with 3y squared. This 3 cancels, I'll have a 4, and then one of the y's will cancel out entirely here. So now what do we have left? 4x times 2x, so that's 8x squared over y. And then this is all over 9y to the 4th. And no, of course we can't leave it like that. It's a complex fraction. You can't have a fraction in a fraction. Heavens to Betsy. So multiply everything by the LCD, which is y, to clear it out. And then let's see, now we'll have 6y cubed minus 8x squared over 9y to the 5th. Can we factor anything out of the numerator? Just a 2, right? So I'm just going to rewrite the second derivative is 2 times 3y cubed minus 4x squared over 9y to the 5th. And sometimes your original function pops back in when you find the second derivative. So let me just check. This is not boxing nicely. Come on, we're proud of it. Good. Let's just check what the original function was. X squared minus y cubed. Do you see x squared minus y cubed? No. If we did though, what you would do is replace it with a 6. Yep, you would. So just be on the lookout. How did I know to look out for that? Why, I've done so many problems in the course of my life. That happens. Okay, very good. Now, implicit differentiation is one technique. We're going to revisit it in just a little bit when we do related rates. Another one is logarithmic differentiation. Couple scenarios when you want to use it. One is when you look at the function, like say they weren't nice, they didn't tell you use logarithmic differentiation. If you look at it and you're like, my, that would be cruel and unusual punishment to take a derivative and have to do not only chain rule, but the most obnoxious quotient rule and product rule within it. I mean, why? Why? What's the point? then I think to myself, oh, perhaps logarithmic differentiation is the way to go. I really do think those things to myself. Okay, so to start off, you take the natural log of both sides. So ln of y equals ln of, and then I'm already going to get going because I know I want to use my log properties to rewrite this nicer. So instead of cube root, I'm going to rewrite the argument raised to the 1/3 power. All right. And the whole point of doing that is so I can move that 1/3 exponent to the front of my natural log. So we have ln of y equals 1/3 times, and then expand your logarithm further into 4. So we'll have ln of 3x plus 1 plus, that 2 is also going to move to the front, ln x plus 4 minus ln x to the 4th plus 6 minus ln x plus 8. If you need a review of your logarithm properties, I'll link a video here for you. And then now that everything's nicely expanded, it's time to take the derivative. So derivative of the left-hand side, always going to be the same. Derivative of ln of y is 1 over y, but then we use the chain rule, so times dy dx. And then we have over here 1/3, that just hangs outside. You don't do product rule when you just have a constant times something. The constant just comes along for the ride. Whee! So derivative of ln 3x plus 1 is going to be 1 over 3x plus 1. And then when you use the chain rule, you have to multiply by the derivative of what's inside. So what's the derivative of 3x plus 1? Oh, good. It's just 3. Plus, and then I'm going to have 2 over x plus 4. Derivative of x plus 4 is just 1. Minus derivative of ln of x to the 4th plus 6. You're going to put x to the 4th plus 6 in the bottom. Derivative of x to the 4th plus 6 is just 4x cubed. And then the last term, derivative of that is minus 1 over x plus 8. Okay? Good. Only thing left, we have not gotten dy dx all by itself. There's 1 over y still over there. So multiply both sides through by y. So it'll cancel. See how lovely. And then now we have dy dx equals 1/3. I'm not going to write y. I'm going to replace y with how it was originally defined in the problem. And I'll write the cube root because that's how they wrote it when they gave it to me. So I'll give them back what they gave me. Cube root of 3x plus 1, x plus 4 squared, over x to the 4th plus 6, x plus 8, and then we have 3 over 3x plus 1 plus 2 over x plus 4 minus 4x cubed over x to the 4th plus 6, blah, blah, blah. Typically, when you find a derivative, you need to get a common denominator. But with these, when you do logarithmic, usually it's not necessary because it would just make more of a mess of things. And most of the time, we just want to see that you know how to apply your logarithm properties and proceed with the derivative appropriately. So I don't require my students to get a common denominator for these kinds of problems. Just check with your instructor, but it should be fine if it's like this. The other time when you absolutely have to use logarithmic differentiation to take the derivative is when you have variables in the base and exponent of your function, like the following example. See how you have cosine x, not just a constant in the base, and the variable x is the exponent. So you have to take the natural log of both sides. And we do this so that, again, we can move that x to the front and multiply it by ln of cosine x. So we have ln of y equals x times ln of cosine x. Okay, now you should be able to take the derivative, no problem. Derivative of the left-hand side, derivative of ln of y is 1 over y times, use the chain rule, dy dx. Now look at the right-hand side. Be careful. We have a product of two functions, don't we? X is one function. Ln of cosine x is the other one. So product rule time. Derivative of x, 1. Leave ln of cosine x alone. It's not his turn. Plus, now I leave x alone. X already had its turn having its derivative taken, okay? Now it's ln of cosine x's turn. Derivative of ln something is 1 over the something. And then don't forget the chain rule. I have to multiply by the derivative of the something of cosine x, which is, good, negative sine x. Love it. Okay, let's clean this up. 1 over y dy dx equals ln of cosine x. This is minus, yes, because I took that negative out, and then check this out. Sine x over cosine x, that's tan x, okay? So this is x tan x. Do you have to replace sine x over cosine x with tan x? You betcha, okay? Say someone comes up to you and says, oh, now I want a second derivative. You don't want to be the sucker doing quotient rule because you left it sine x over cosine x. No, you want to write it as tan x so you can be done with it in one step. Okay. Anyways, last step, multiply by y. Multiply by y. So then now we have dy dx equals, well, I'm certainly not going to write y. No. I'm going to replace it with cosine x to the x. And I'll put that in the front. It'll look better. So cosine x to the x times ln of cosine x minus x tan x. All right. That's a good one. I like that one. Okay. Very nice. I told you what was coming next. Are you ready? Related rates time. Here's a few things to keep in mind with related rates. You will always take the derivative of whatever equation you write with respect to t. Write that down. You will always take the derivative when doing a related rates problem with respect to t. It's a rate. Rate is how something changes with respect to time, okay? So here we go. A piece of land is shaped like a right triangle. Okay. 2 people start at the right angle of the triangle at the same time. And they walk at the same speed. Wow. Along different legs of the triangle. Here they are walking. One's going this way. One's going this way. Same speed, mind you. Okay. If the area formed by the positions of the 2 people and their starting point, the right angle, is changing at 5 meters squared per second, then how fast are the people moving when they are 4 meters from the right angle? Round your answer to 2 decimal places. Okay, what I do is I always look through and see what quantities they gave me. 5 meters squared per second. That's a rate. I got to figure out what derivative that is. Look at the units. Meters squared. Anything squared is area, right, per second. And they even told me, for crying out loud, area. So that's dA dt is 5 meters squared per second. The units match up. Area, meters squared. T, seconds. Bam. What are they asking for? How fast are the people moving? So what do they want? You have to figure out what derivative they want. How fast are they moving? So that's the rate of change at which this length or this distance that they're traveling is changing. I haven't put any variables down, so let's do that. Now, the interesting thing is, what makes the problem easy is that they told me they start at the same time and they walk at the same speed. So whatever distance one of them covers, the other one's covering the same thing. So these distances are equal. I'm just going to call them both x. So if they want the speed at which the people are moving, how fast they're moving, what the problem is asking for is for us to find dx dt. Okay. And then they said when they are 4 meters from the right angle. So that they want dx dt when x equals 4. You are going to plug in x equals 4 at the very end. They will always give you a specific piece of information that corresponds with a precise moment in time. You save that for the end. Don't get too excited and plug it in prematurely, okay? So your job now is Ignore the derivative portion. Look at the variables at play, x and a. And we're talking about a triangle. Can you think of a formula that relates the area of a triangle with its sides? Don't worry about the calculus. Just, do you know the formula for area of a triangle? I do. I hope you do. Area of a triangle is 1/2 base times height. But in this particular case, since the base and height are both x, this is 1/2 x squared. Boom. That's what we're going to use. Yeah, that's it. And it's a related rates problem. So I'm going to differentiate both sides of this equation right here with respect to what variable? I said it at the beginning. Did you pay attention? I'm going to differentiate both sides with respect to t. Always and forever. It's a related rates problem. Okay. So derivative of a with respect to t is 1 times dA dt. Yeah, implicit. Derivative of 1/2 x squared. The 2 and the 1/2 will cancel, so I'm just going to have x times dx dt. See, if I had plus t cubed and I took the derivative, it would just be plus 3t squared, and then dt you don't see, so we don't write it. But none of these variables are t's, right? None of the variables are the ones with which we're differentiating with respect to, so that's why we have to do implicit rules, right? Okay, enough of that. So they want dx dt. Let's get it by itself. Dx dt equals dA dt over x. And then they told me dA dt is 5 meters squared. And then x, now I get to use it. Oh my God, when x is 4. They said round to 2 decimal places. I'm not sure why. 5 over 4 is 1.25, but okay. So let's summarize. Dx dt is 5 over 4. What would the units be? Well, x is being measured in meters, and t is measured in seconds. So this is meters per second, or they wanted decimals, so I'm going to give them what they want. Yes. Okay. There we go. See, not so bad. Not bad at all, actually. Let's obviously take the spice level up. Are you ready? Yes. Water is being drained from a container which has the shape of an inverted right circular cone. It looks not like that at all. Holy moly. Okay. Forget it. I'm going to draw my own because I'm good at drawing. Okay. Here. Inverted right. This is a right angle, circular cone. Base is a circle. The container has a radius of 2 inches at the top and a height of 5 inches. At the instant when the water in the container is 2 inches deep, so when that's at 2 inches, the surface level is falling at a rate of 1.9 inches per second. Find the rate at which the water is being drained from the container. Ooh, okay. So water's draining out. And this one's interesting because as the water's draining out, 2 things are changing. The water level, the height here is changing, and also the radius, right, is decreasing. So 2 quantities are changing. I'm gonna label at any arbitrary moment in time where the water is and say that the water level, I'll just call it H, and then this radius is R. Both of those change. When it's all the way full, the radius is 5. No, the radius is 2 and the height is 5. But since the water's draining, R changes, H changes, okay? Here they told me the surface level is falling at a rate of 1.9 inches per second. So which quantity would that represent? Surface level. That's the rate of change of the height, yes? So they just told me dH dt, since it's falling, it's negative 1.9 inches per second. Yeah, and then what are they asking for? Find the rate at which the water is being drained. Water being drained, they want the change in volume. They want dV dt. You need to be mature enough to read that sentence and understand that that's the quantity they're after, okay? So, what did we do last time? We just focused on the variables V and H, and we said, okay, can we think of an equation that relates the two of them? So you do need to know the formula for the volume of a cone. No, it's not that obscure. No, it's not that unreasonable to be asked of you, okay? It's gonna come up quite often in your calculus career, so just memorize it. So volume of a cone is 1/3 area of the base times height. So it's 1/3. This base is a circle, so it's pi r squared, and then the height is h, okay? But we have a slight problem here, people, because how many variables are in this equation? I just put down V, R, and H. And they gave me dH dt. I want dV dt, but this R is going to be a problem because I'm going to have a dr dt if I take the derivative, and I can't have two unknowns to solve for. Oh me, oh my. So what we do is, we set up similar triangles. Remember when the cone's all the way full, the radius and height are 2 and 5 inches respectively. As the water's being drained, we have a similar little right triangle that represents the arbitrary radius and height, okay? So similar triangles are in proportion, meaning I can write that 2 over 5 is equal to r over h. And remember, we want to get rid of this variable because we're only trying to work with h's and v's. So let's cross multiply 2h equals 5r. So 2/5 h is r. And then we should be good to go. So now let's rewrite our volume equation. V equals 1/3 pi. Instead of r, I'm going to write 2/5 h squared times h. You guys, the worst is over. I promise you. I promise you. So V equals 2/5 squared is 4 over 25. And then I have pi over 3. So I'm going to write 4 pi over 75h cubed. Yes. Okay. And then now it's time to take the derivative with respect to t. Always t. It's a related rates problem. Always t. d dt, d dt. All right, derivative of the left-hand side is just dv dt. 4 pi over 75, it's gross, it's just a constant. Just bring it down and then pay it no further attention. What's the derivative of h cubed? With respect to t. Why, it's 3h squared times dh dt. Good. What do they want? Oh, they wanted dv dt. Okay, great. So, yeah, I want to cancel this. I do. This is 25. So dv dt equals 4 pi over 25 h squared times dh dt. And they told me dh dt was negative 1.9. Did they not? Inches per second. And h, what am I plugging in for h? Oh, right here. At the instant when the water in the container is 2 inches deep. So that means when h is 2. Now's the time to plug it in. H is 2. All right. So dv dt is going to equal 4 pi over 25 times 2 squared times negative 1.9. And then they told us we could round. Okay, let me get my calculator out. If your instructor was not going to let you have a calculator, they probably would not use 1.9. You know what I mean? Times negative 1.9, and then divide all of that by 25. And I got negative 3.82. Find the rate at which the water is being drained from the container. So I'm just going to leave it negative 3.82 dV dt. That's going to be inches cubed per second. all right? So the key thing to remember, whenever you're working with related rates problems, you need to be able to translate whatever information they give you, right, into a derivative appropriately. And then from there also, you need to keep in mind your units because they are very helpful. They'll clue you in on a lot of things as to what quantity is being represented, etc. So the units are big. Now, some instructors are going to want you to carry the units all through the equation while you're working with it. I'm not so into that. But if that's what your teacher wants, then do it. You know what I mean? No sense sacrificing points over your ego. Okay. Very good. Now we're going to move on to the next unit, which has to do with finding local extrema and figuring out information about graphs of functions. So we're going to shift gears a little bit, but it ties in nicely. We're asked to find all of the critical points for the following function. So f of x equals negative 6x over x plus 2. So when you're finding critical points come from two places. They come from where the derivative is equal to 0 and where the derivative does not exist. So basically, to start off, you need to figure out what the derivative is. Okay. Now, f prime of x, we need to use the quotient rule. So we have low is x plus 2, d high, negative 6, derivative of the numerator, minus high, d low, derivative of the denominator is just 1, over low. Okay, good. Let's clean it up from here. So in the numerator, I'll have negative 6x minus 12 plus 6x over x plus 2 squared. And then that's just going to simplify and give me negative 12 over x plus 2 squared. Okay, no problem there. Now, when you look at it a little bit further, you notice that the numerator is just a constant. So that means that the numerator is never going to be 0, right? So the first place when you're looking for critical values is, where does f prime of x equal 0? Nowhere, so we have no critical values from there. What about where f prime of x does not exist? Well, that would mean the denominator would equal 0, which would mean x plus 2 equals 0, which means x would have to equal negative 2. But that's not going to be a critical point either, because notice the domain for my function is all x's except for negative 2. Why do I say that? Because negative 2 would make the original function undefined. So you can't have a critical point that's not even in the domain of the original function. So I would say this is not an element of the domain. So there's no critical points from where f prime does not exist. So what does that mean for f of x? It has no critical points at all. Oh, how sad. Don't feel sorry for it. That's just life sometimes, okay? Don't feel sad. F of x has lived a good life. Okay, let's look at another example. This one won't be so depressing, perhaps. We have y equals 4x squared minus 128 rad x. Let's write the domain in the beginning, maybe so we're always keeping it in the forefront of our mind. So what's the domain? Well, 4x squared, that's fine, but I noticed the square root of x, we can't take square roots of negative numbers. So the smallest number I can plug in for x is a 0, all the way to positive infinity, but nothing negative. Let's keep that in mind. Okay, let's go ahead, take the derivative. So y prime, derivative of 4x squared is 8x, very good, minus 128, derivative of square root of x is 1/2 x to the negative 1/2. So this is going to be 8x minus 64 over square root of x. And no, we don't leave it that way. We get a common denominator. So I'm going to multiply 8x by rad x, top and bottom. And then now I have y prime equals, I'm going to write 8x to the 3/2 minus 64 over square root of x. Box it. That's beautiful. Okay, critical points come from two places where the derivative equals 0. So that would mean the numerator is 0. That would mean 8x to the 3/2 minus 64 is 0. That would mean 8x to the 3/2 is 64. So x to the 3/2 is 8. How would you solve that? Well, to get rid of the 3/2 power, you would raise both sides to the reciprocal, to the 2/3, right? Good. When you raise something to the 2/3, you take the cube root and then square it. So cube root of 8 is 2, and then square it, it's 4. Is that in the domain? Yes. So it looks like that's going to be a critical value. When I find the y value that corresponds, f of 4, that's 4 times 4 squared minus 128 times square root of 4. I'm going to get negative 196. So yay, I already got a critical point. At 4, negative 196. Okay, I'm not done. Critical points also come from where the derivative equals 0. I said that already. Where the derivative does not exist. Okay. If it doesn't exist, that means the denominator is 0. If rad x is 0, that means x is 0. Is that allowed? Is 0 in the domain? Yes, it is. It is. You can take square root of 0. There was no variable in the denominator in the original function. There was just a square root sign, but that's fine. That's fine. So if x is 0, what is y going to be? F of 0 is 4 times 0 squared minus 128 times 0, so 0. So 0, 0 is the other critical point. And that's your final answer. So when they say critical point, they want an actual point, like an ordered pair. So go find the y value. If they just want a critical value, then usually you can just give the x value, right? I'm just always especially paranoid, so check with your instructor what they want. Okay, good. Now a couple theorems. We have the extreme value theorem, and that tells us the following. So if f is continuous on a closed interval from a to b, then that means f attains an absolute max value and an absolute min value. So you will always be able to find both an absolute max and absolute min for a function that's continuous on some closed interval. If you don't have a closed interval, though, you may not have an absolute max. You may not have an absolute min, okay? And if the function's not continuous, also not true. So those two things have to happen. Closed interval, continuous function, but then you can for sure find both. So here's the process. If you're asked to find an absolute max and an absolute min, and they're giving you a continuous function, you have a closed interval. First thing, you find the critical values. We just did that. You know how to do that. You also, if they're not critical values, figure out what f of a is and what f of b is. So you find out the function values at the endpoints of the interval. And then you just look through and compare. The biggest function value from all the critical points and the endpoints is your absolute max. The smallest one is your absolute min. Once you see an example, it's going to be easy squeezy, I promise. So here we go. Find the absolute extreme values of the function on the interval. So the function that they gave us is natural log of x plus 2 plus 1 over x, and the interval is from 1 to 6. Okay? Good. Let's list the domain of f of x just to start off with. You can't take the natural log of anything that's not positive. So x plus 2 has to be strictly greater than 0, so x has to be greater than negative 2. And also 1 over x can't be 0. Okay, so the domain is x such that x is greater than negative 2 and x can't be 0. Okay, cool. We'll keep that in mind while we find our critical values. We might have to throw some away. So let's get critical values. F prime of x, derivative of ln of x plus 2 is going to be 1 over x plus 2 times derivative of x plus 2, which is just 1. And then the derivative of 1 over x, well, remember, 1 over x is x to the negative first, right? So that derivative is just going to be negative x to the negative second. Oh, okay. So f prime of x is 1 over x plus 2 minus 1 over x squared. And you betcha we're going to get a common denominator. So I'm going to multiply the first term by x squared, second one by x plus 2, those parentheses are life-changing, over x plus 2 times x squared. And then I'm left with x squared minus x minus 2 over, let's write x squared and then x plus 2 only because it looks nicer. All right, just being real. Okay, so here we go. Critical value time. Oh, I didn't mean to do that. Okay, so critical values come from two places. What are they? Do you remember? Where f prime of x equals 0, that happens when the numerator is 0. If you forgot to put parentheses, then this wouldn't be negative, and you would be panicked because it wouldn't factor. But it factors. X minus 2, x plus 1. Woo! Right? So x equals 2, x equals negative 1 are both critical values. Are they in the domain? 2, yeah. Negative 1, yeah. But my interval is only from 1 to 6. That's A and B, like this. 1 to 6. That's A. That's B. 2 is okay. 2 is on the interval, but negative 1 is outside the interval, so we're not using that one. Other place you get critical values is where f prime of x does not exist. That would mean the denominator is 0, x squared times x plus 2. So let's see, that would mean x is 0 or x is negative 2. Are those in the domain? 0 is not in the domain. That's not in the domain. Negative 2, no, that's also not in the domain, nor is it in the interval. So we only have one critical value. That's fine. Just make yourself a cute little table now. It's table time. X, you know what, let me put it beneath here. X, f of x. And I'll just remind you, f of x was ln of x plus 2 plus 1 over x. And the interval was from 1 to 6. So you list those, and then I'm going to add to that whatever critical values I find that are within the interval and see what the function values are. The original, not the derivative, the function values. So let's see, ln of 1 plus 2, that's ln of 3 plus 1. Okay, ln of 3, I don't know if your teacher lets you use a calculator or not. But anyways, just in case, this is about 2.1. F of 6, that's going to be ln of 8 plus 1/6. So ln of 8 plus 1/6, that is about 2.24. So I'll just say 2.2. And then f of 2, that's ln of 4 plus 1/2. So ln of 4 plus 0.5 is 1.9. So, well, it's 1.88, blah, blah, blah. Okay, so you can see clearly, here's our absolute max, and here's our absolute min. Now, check out what happened. The critical value gave us the absolute min. The absolute max just came from one of the endpoints. Okay, so that means it's not a local extrema, but it just ends up being an absolute max because it's the endpoint of the graph. So on 1 to 6, that's the biggest function value you get. We're not talking forever on the graph. How do you write your final answer? Not like this. Ew. Show some respect. So I would write absolute max occurs at f of 6, which is ln of 8 plus 1/6. The decimal was just for you, unless your teacher asks for it. And then absolute min, f of 2, ln of 4 plus 1/2. And then you box that with such pride. Like, I am a stellar calculus student. Check me out. Okay, good. Really good, you guys. All right, I got a couple more theorems for you. Mean value theorem and Rolle's theorem. Rolle's theorem sounds like it's a special case of the mean value, but it's actually the opposite. Anyways, one came first, the other came after, and it's not the way you would think. It doesn't matter. Just remember the statement. Rolle's theorem has one extra condition. Mean value only has two. If f of x satisfies the following, it needs to be continuous on the closed interval from a to b, differentiable on the open interval. Then there is a number c. Pay attention, c has to be on the open interval, a to b, such that f prime of c equals f of b minus f of a over b minus a. What that says is there's a point on that interval where the slope of the tangent line is equal to the slope of the secant line that cuts through the endpoints of the interval on the graph. If you want a more in-depth explanation, you can watch the lecture video I have on the mean value theorem, but I'm guessing you're reviewing for finals. Time is of the essence, so let's just cut to the chase. Rolle's theorem just has one extra condition, that f of a is equal to f of b, so the function values are equal on the endpoints, and I'm sure you can imagine if these guys were equal, then you would just have a 0, yes, in the numerator, and that's what it says, f prime of c is 0. Okay, I'm going to do an example that ends up being a hybrid of the two. So find the value or values of c that satisfy the equation in the conclusion of the mean value theorem for the function and interval. And you have to always first verify the conditions before you proceed, so let's do that. So first thing, I need to show that f of x is continuous on a to b. So is f continuous on 3 to 4? Well, how do you show that? Well, we have a three-part definition of continuity, but that's only to test continuity at one point. How would you test the entire interval from 3 to 4? You can't, not using that definition. Instead, you use the theorem that I listed after. This is all in the part 1 review video that says that polynomials, rational functions, trig, exponential, etc., they're all continuous on their domain. So as long as we can identify what kind of function we have and what its domain is, I know it's going to be continuous there. So that's how we're going to show that it's continuous on 3 to 4. So can you tell by looking at f of x what kind of function it is? I see x. That lets me think it's a polynomial, which it kind of is. And then 12 over x, that's a rational function. So basically f is a rational function. But if you want to say it's a polynomial and a rational function, that's fine. So by our little theorem, which doesn't have a name, so I'll just write theorem, f is continuous on its domain. What's its domain? Certainly not all real numbers. 12 over x, x cannot be 0. So the domain is x such that x isn't equal to 0. Well, 3 to 4, that does not contain 0, so we're good. So this tells us f is continuous on 3 to 4. We're good to go. How do I show that f is differentiable? You can do this cute little abbreviation, differentiable, on the open interval from 3 to 4. You check the domain of the derivative. So let's go ahead and do that. Let's take the derivative. So f prime of x, derivative of x is 1. What's the derivative of 12 over x? Can you do it in your head? 12 over x is 12x to the negative first, right? So the derivative would be minus 12x to the negative second. Let's rewrite it as 1 minus 12 over x squared. Well, what kind of function is this? It's also a rational function. So by our theorem, it's continuous on its domain. And it actually has the same domain as f, everything except 0. So is it going to be differentiable on 3 to 4? Of course. Great, so that means we can go ahead and apply the mean value theorem. So this means there exists So you could write there exists, or you could use this symbol, a number c that belongs to the interval from 3 to 4, open interval, such that f prime of c equals f of b minus f of a over b minus a. Now, f prime of c, lucky for us, we already differentiated f of x earlier. So all I have to do is rewrite it and replace that x with a c. Yes, it matters. And then f of 4 minus f of 3. That comes from the original function. So where was f of x? F of x is x over 12 plus x. Okay, so let's f of 4. F of 4 is 4 plus 12 over 4. 4 plus 3, that's 7. And then f of 3 is 3 plus 12 over 3, that's 3 plus 4, that's 7 also. Oh, how funny. So that's 0 over 1, that's just 0. Don't have a panic attack. Let me add a page. I feel like we need it. I get stressed when there's not enough room and then I make mistakes. We don't want that. Okay, 1 minus 12 over c squared equals 0. So really, if they told us to use Rolle's theorem, we could, right? Because f of a equals f of b. So let's move that 12 over c squared over, multiply by c squared, and then square root of both sides. Rad 12 simplifies to 2 rad 3. But remember, c has to belong to the interval from 3 to 4. So sometimes you will have more than one value of c as your answer, but in this case, I can't use negative 2 rad 3. That's not on the interval from 3 to 4. So only c equals 2 rad 3 is on the interval from 3 to 4. So that's the only one you're going to report. Now, here's something that's important. Like, just think about it. You might say, oh, then I'm not going to put the plus or minus. I'm just going to jump straight to plus 2 rad 3 because I'm not going to use the negative. But you know what? That doesn't show that you thought about it. Maybe you're just some careless little schmuck who forgets that when you take the square root, you need a plus or minus. So if I were taking this test, I would put the plus or minus. In fact, I tell my students to. And then specifically, explicitly mention that you thought about the fact that c has to belong to the interval, open interval from a to b. And that's why you're choosing only the positive. And you have to go about taking your test like that too. This is just general test taking tips, okay? When you take an exam, if you think about something and it was important to solving the problem, write it down. Let your instructor know. Don't let them think that you just stumbled upon the right answer or you were sloppy and lucked out, you know? If you are thinking things, let it be known. Don't be too lazy to write it down. This is you showing evidence that you deserve whatever grade you think you deserve. I'm sure most of you think you deserve an A. Whether or not that's true, that's another thing, but put that evidence out there, okay? All right, good. Now we're gonna do a monster graphing problem because I'm a beast and I'm in the mood for it. So here we go. Use the guidelines of section 4.5. That's what it is in our book that we use. Probably most of you use Stewart Calculus, and I think right now it's still section 4.5. To graph the equation, include the coordinates of any local and absolute extreme points and inflection points. I'm not so cruel to my students when I give them these questions. I'll specifically say what I want. So I'll say like, step 1, give me the domain. So I'll walk you through. The domain, it's a rational function, so all I got to make sure is that the denominator is not 0. X squared plus 16, that can't be 0, right? That's never going to happen. So the domain is actually all real numbers, negative infinity to infinity. The next thing I ask them to find are intercepts, x and y. So x-intercept comes from setting the function equal to 0, which is basically just setting the numerator equal to 0. So I get 0. And then if I plug in 0 for x, you'll still get 0, 0. So that's the x and y intercept. Then we're going to need asymptotes. Shall I number for you? Okay, 1, 2, 3. Asymptotes. So I let my students just get the vertical asymptotes by looking at the denominator. you know, after they've reduced the rational function. Some teachers might want you to find the limit. If they're going to be that rigorous, then I suggest you watch my videos on graphing functions. I'll link a couple here. But I can tell the denominator is not going to be 0. So let's just find horizontal asymptotes. And for that, we always take limits to infinity. So as x goes to infinity, 16x over x squared plus 16. I'm going to divide by the highest power of x in the denominator. So this is going to be the limit as x approaches infinity of 16 over x over 1 plus 16 over x squared. And as x goes to infinity, 16 over x is going to go to 0. So will 16 over x squared. So this is 0 over 1 or just 0. And there would be no difference if this was positive or negative infinity. So I don't need to repeat this process. I have one horizontal asymptote only at y equals 0. Make sure you write y equals to show that it's horizontal. And there's no vertical asymptotes. The function's already in lowest terms and the denominator's never 0. Okay, from there I would ask them to find f prime and any critical points. So let's go ahead and do that. I'll just remind you, f of x was 16x over x squared plus 16. Okay, so let's go ahead, take the derivative, quotient rule time. F prime of x is going to be low d high. What's the derivative of the top? Just 16. Minus high, what's d low? 2x, very good, over low. Okay, I'm going to factor out this 16, yes. And then what am I left with? X squared plus 16 minus 2x squared over x squared plus 16 squared. Oh, how snazzy. And then I can combine some like terms in the numerator. So I've got 16 times 16 minus x squared over x squared plus 16 squared. Good. There's my derivative. So critical points, where do they come from? Or critical values? Where the derivative equals 0. So that would mean the numerator is 0, right? I don't need to just use that 16. Just when 16 minus x squared is 0, that means x squared is 16. So x equals plus or minus 4. And also where f prime of x does not exist, that happens when the denominator is 0. But remember, x squared plus 16 can never equal 0. So that's not happening. Okay, good. From here, let's find our local extrema. So what was that? Step 4. Let's do step 5. Local extrema. How do we find those? Using the first derivative test, we make a number line. I like to label it. That way you know where to plug in when you're testing your intervals. So I'm going to break it up at -4 and +4 because those are the only critical values I have. And I'm plugging them into the derivative. So if I test a value from -infinity to -4, pick something in there, say -5. Okay. This is positive. 16 minus -5 squared, that's going to be 25. So this is negative. So I've got positive times a negative, and then the denominator is always positive, right? So the derivative is negative here. So the function is decreasing. Now pick somebody between -4 and 4. How about our good friend 0? I love testing with 0. Okay, I don't even need to write anything out. Positive, 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 positive. Lovely. The function is increasing. Pick something bigger than 4. How about +5? positive, negative, positive. So negative. The function's decreasing here. So I can tell right by looking, I have a local min at x equals -4 and a local max at x equals 4. I can tell it so easily because of the way I drew the arrows, right? Doesn't it look like a min? Woo! Doesn't it look like a max? Yes. So that's how my Calc 1 teacher taught me over 20 years ago. And bless him, because it's working for me, let me tell you. Okay, let's write out the intervals of increase, decrease, and then we'll also figure out what the y-coordinates are for the extrema. So the function is increasing from -4 to 4 and decreasing from -infinity to -4 and 4 to infinity, okay? And local min is at f of -4. F of x was 16x over x squared plus 16. I'll just tell you what it comes out to. -2. And local max is at f of 4, which is +2. Okay. Good. Now guess what it's time for? The second derivative and inflection points. Oh yes. So we need f double prime of x and inflection points. So to get the second derivative, we need to remember what the first derivative was. It was 16 times 16 minus x squared over x squared plus 16 squared. So we are going to have to use the quotient rule again. Are you going to be okay? I hope so. Here we go. F double prime of x time. I did make a video on just how to simplify the second derivative when using the quotient rule. I'll link it here. Here we go. Low. D high. Be careful. When you take the derivative of the numerator, you don't need to do product rule. No, because that little 16 right here, it's just a constant. So just bring it along for the ride. You don't need to do product rule. So derivative of the numerator is just 16 times, now derivative of 16 minus x squared, that's -2x, okay? So that's low D high minus high D low. Okay, we got to do chain rule. So it's x squared plus 16 squared. Derivative of something squared is 2 times the something to the first. I'm going to leave this x squared plus 16 alone. And then derivative of x squared plus 16 is 2x. Okay, okay. Over low, low. Good. No, you don't go on a foiling frenzy. You factor out the GCF from the numerator. Otherwise, you will go crazy, and you probably won't be able to simplify the second derivative appropriately to find your critical values. So what's the GCF? Yeah. I'm thinking we can take out -32x. Yep. And we can take out 1x squared plus 16. Only one of them. 16 minus x squared is not the same as x squared plus 16. It might sound stupid to some of you, but I have to remind students of that from time to time, so I figured it was worth mentioning. Okay, so I'm taking out -32x and an x squared plus 16. There's two terms going on. Here's one, here's two. So what's left here? I've taken out one of these and all of this. So I just have 1x squared plus 16 left. What's left in the second term? I took out the negative. I took out the 16. I took this out. I took this out. All that's left is a 2 and a 16 minus x squared, and it's not even negative anymore. Okay. See? Over x squared plus 16 to the 4th. Already, so much better. Don't you feel less stressed? This cancels with one of the x squared plus 16s in the denominator. Let's clean up further. So we've got -32x. This is x squared plus 16 plus 32 minus 2x squared over x squared plus 16 cubed. And then we just have to combine like terms. We made it. F double prime of x negative 32x times, this is going to be 32 plus 16, 48 minus x squared over x squared plus 16 cubed. Whew. If you got that, you guys, give yourself a little pat on the back. Yes, way to go. Okay, we're going to add a page in here. Now, to get the possible inflection points, it's very similar to when you find critical values, critical points. You check where the second derivative is 0 and where it doesn't exist. So f double prime of x equals 0, or f double prime of x does not exist. So if the second derivative is 0, either negative 32x is 0 or 48 minus x squared is 0. So either x is 0 or x squared is 48. So x equals plus or minus square root of 48. 48 is 16 times 3, so that would be 4 rad 3. F double prime doesn't exist. That would mean the denominator is 0, but we know that can't happen. So our possible inflection points could happen when x is 0 or plus or minus 4 rad 3. So now, much like when we found local extrema, you're going to make another number line for f double prime of x and list those values that we just found, negative 4 rad 3, 0, and 4 rad 3. I'm going to test, this time I have, see, 1, 2, 3, 4 intervals to test, and you're going to plug them in where? The second derivative, up here, right up here. So negative 4 rad 3, just if you want to know for testing purposes, right, as a decimal, where are we at? Rad 3 is about 1.7, but anyways, negative 4 rad 3, that's going to be about negative 6.9. And so positive 4 rad 3 would be about positive 6.9. Okay, so let's see here. If we're testing something over here, say I use negative 10, right? That feels safe, negative 10. So negative 32 times negative 10, that's positive. 48 minus negative 10 squared, that's 48 minus 100, that's going to be negative. And then, you know what? The denominator is always positive because we're squaring something, we're adding to it, and then we're cubing it. Who cares? This is already positive. It's staying positive. So I know, don't worry about the denominator. It's always positive. So that means the second derivative is negative in this interval. What does that tell me about my graph? That my graph is concave down. Okay. What about between negative 4 rad 3 and 0? Maybe you want to test with negative 1 in your head? Okay, sounds good to me. So if we're using negative 1, oh, I didn't mean to erase. Okay. Negative 1 times negative 32, that's positive. 48 minus 1, that's positive. We know that's positive. So positive, that means the graph is concave up. Between 0 and 4 rad 3, say we use positive 1. This will be negative. This will be positive. Negative times a positive is negative. And then bigger than 4 rad 3, say I use positive 10. Negative, negative. That's always positive, we established. So a negative times a negative, that's positive. Second derivative is positive, which means my graph is concave up. Okay, so we've got a lot of inflection points. Inflection points happen anytime there's a change in concavity in the graph, as long as that point's in the domain. So inflection points at all 3 of these x values. Let's list our intervals of concavity. The graph is concave up where? From negative 4 rad 3 to 0, as well as 4 rad 3 to infinity. And then it's concave down where? Woo. from negative infinity to negative 4 rad 3 and 0 to 4 rad 3. And inflection points, so f of negative 4 rad 3, those go in the original function. I'm just going to tell you it's negative rad 3. And then f of 0 is 0. And f of 4 rad 3 is positive rad 3. So now we have everything ready to put our graph together. Hopefully you jotted everything down. I have it on a scratch paper off to the side, so I'm not going to keep scrolling up and down. We found our intercepts, and I'm just going to scale out maybe to 10. I'm scaling by 2s. I hope you're okay with that. 2, 4, 6, 8. And then negative 2, 4, 6, 8, 10. 2, 4, 6, 8. Okay, list everything relevant that you found. So like we found our intercepts. There was only 1, 0, 0. We found horizontal asymptote at y equals 0. So I'm just going to remind myself that it's there. And then list your local extrema. So if you'll remember, I don't. We had a local min. I'll just write it down. Local min was at negative 4, negative 2. And local max was at 4, 2. Okay, so negative 4, negative 2, 4, 2. And then we have inflection points as well. We already know negative 4 rad 3 is about negative 6.9, and then negative rad 3 is about negative 1.7. And then 6.9, 1.7, and 0, 0. Those are all inflection points. So show them, or do your best to show them. So negative 6, 2, 4, 6, and a wee bit more, negative 1.7. There's an inflection point. And then on the other side, 2, 4, 6.9, positive 1.7, maybe right there. I would write IP just in case, it's hard to sometimes draw a change in inflection very perfectly. So if you want to label it, it's not bad. I think it's pretty easy to see what the shape is. Hopefully you can. It's changing concavity here as well. So let me label. This is an inflection point. The graph is concave down from 0 to 4 rad 3. So it looks like sad parabola, downwards parabola right here. The max happens naturally, so don't go higher than the max. And then it stays concave up the rest of the way, trails off. And then it does the same sort of thing over here. This is actually an odd function. I didn't test for symmetry. You could if you want. If your instructor wants, then you better do it. And that concludes the graph. Okay, I'm going to call it a night. I'm a little tired. I did this actually all in one run. Can you believe it? I didn't have to cut or edit. I did think of something I wanted to say earlier and I didn't. So I'm just going to say it now. If you've stuck around since that timestamp, when we did the related rates word problem, I am going to scroll up. And it asked at what rate the water was being poured out. Drained. This has been bothering me. Drained already implies that it's being taken out. It's negative. So you probably should just say it's being drained at 3.82 inches cubed per second. You know what I mean? If they just said, what's the rate of change of the water in the container, then you would say negative, because rate of change is neutral. It could be going up, could be going down. But drained already implies that it's decreasing. So I would take the minus out. It's a little subtle, but it's been bothering me and I didn't want to edit. So here we are. Anyways, I actually did have a few more because we didn't even talk about integration. So I feel like we need a part 3. So it'll come soon. Soon enough for your final? I'm not sure. I hope so, but I'm going to do my best. So give this video a thumbs up. If you stayed till the end, you are the MVP. Comment, I made it to the end, and I will respond. I promise. That's exciting to me. It's Sunday night. I went to my niece's piano recital today. She killed it. She was phenomenal. She's 8 and she's a rock star. And it's been a long day, but here I am recording for you people because I care and I love you all and I want you to do well on your finals. So if I have it in me, I'll wake up early and do part 3 tomorrow, but I do have to go to work all day and teach, so we'll see. Anyways, I wish you all the best. Lots of luck on your final exams. And stay tuned. I'll still record stuff during break. I love social media. I love YouTube. I love all that sort of thing. So follow me on Instagram and TikTok if you don't already. It's at Math TV with Professor V. Subscribe if you haven't already. Give this video a thumbs up. If you want to support your sister here, you can become a member of this channel. You can also join my Patreon. I'm an Amazon influencer too, believe it or not. You can shop my store. So anyways, stay tuned, you guys. Sending lots of love to you all. I'll talk to you soon. Bye.